We've seen the consequences of trying to solve a system of linear equations. But let's look at one particular method for trying to solve linear equations. The method of Gaussian elimination. The method that we've seen so far to solve systems of equations is an elimination technique. And Gaussian elimination is a specific case of this. We eliminate the variables one by one, we form an upper triangular system, but what distinguishes Gaussian elimination is at each stage, multiples of the first row, or the first row under consideration, are subtracted from the rows lower down. We don't multiply the rows lower down by any particular number. That's what distinguishes Gaussian elimination. So let's see Gaussian elimination as applied to a system of equations here. 4 equations in w, x, y, and z. We start off, we put it into an augmented matrix form. And then we start carrying out row operations in order to try to eliminate the variables. So the row operations that we will carry out, firstly, we want to get zeros in those 3 positions here. So we'll take row 2 minus row 1 to get a 0 here. We'll take row 3 minus 2 row 1 to get a 0 here. We'll take row 4 minus 5 row 1 to get a 0 here. So note that what we're doing, we have 1 of row 1, 1 of row 2 minus row 1, 1 of row 3 plus 2 row 1, 1 of row 4 minus 5 row 1. We never multiply, under Gaussian elimination, we never multiply the row in question by anything. And then we subtract off a multiple of, say, row 1, and that multiple will be the coefficient here divided by the coefficient here. That is Gaussian elimination. And when we do that, yes, we wanted to get zeros in the 3 positions here. The top line stays unchanged, and then we'll actually see that we change, of course, the various coefficients in this part of the augmented matrix. So that's the first stage of the elimination. The next stage of the elimination is to get zeros in the 2 positions here. We've made use of row 1, now we make use of row 2. From row 3 and row 4, we will subtract multiples of row 2. We will subtract 2 over 1 times row 2 from row 3. We'll subtract minus 3 over 1 of row 2 from row 4. That is, we add 3 row 2. And when we do that, we see zeros in the positions here, zeros here and here. Yes, next we'd like a 0 here. And now we subtract a multiple of the 3rd row from the 4th row. So what we're subtracting off here, we take row 4 and we subtract off minus 6 over 2. That is, we add 3 row 3. And you can see now it turns into an upper triangular system on the left. And now one by one we can solve the resulting equations. Here are the resulting equations. 4z is 20 gives us that z is equal to 5. We look at the 3rd equation together with the fact that z is 5. 2y plus 25 is 33. 2y is 8, gives us that y is equal to 4. Now let's look at the 2nd equation, together with the fact that z is 5, y is 4. X plus 16 minus 5 is equal to 10. X plus 11 is 10. X is minus 1. So now let's go to the very first equation. We have values for x, y, and z. So it's w minus 3 minus 24 plus 10 is minus 16. W minus 17 is minus 16. We get that w is equal to 1. So we've solved the system of equations for all four variables. We have values for w, x, y, and z. And of course, we could use any of the equations to check. Probably not recommend the first one because it was used in its original form, but any of the other three, or all of the other three, could be used to carry out a check here. Let's now have an example. Let's solve the following system of equations, 4 of them in P, Q, R, and S. We'll solve them using Gaussian elimination. The first stage is to form the augmented matrix. We take the coefficients, so we have 1p minus 2q plus 3r plus 7s is equal to 3. We have 2p minus 2q plus 10r plus 14s is equal to 8. Minus 5p plus 2q minus 26r minus 36s is equal to minus 30. And then we have 1p minus 6q plus 5r plus 7s is equal to minus 11. So here is our augmented matrix. Now, under Gaussian elimination, one of the things we're trying to do is produce an upper triangular matrix here with the entries under the diagonal being equal to 0. And we do that by taking each of our rows and subtracting off a multiple of row 1. So row 1 remains the same. We're trying to get zeros into the positions here. And then we'll take row 2, we subtract off a multiple of row 1, and the multiple will be 2 over 1. So we have row 2 minus twice row 1. We'll take row 3 and we'll subtract off minus 5 over 1 times row 1. That is, we'll have row 3 plus 5 row 1. And then we'll have row 4 minus a multiple of row 1, 1 over 1. Row 4 minus 1 over 1, row 1. So that is row 4 minus row 1. So those are the row operations we're going to do. First row stays the same. Second row, row 2 minus twice row 1. 2 minus twice 1, minus 2, minus twice minus 2, minus 2 plus 4 gives us 2. 10 minus twice 3, 14 minus twice 7. It's given us a 0, an unexpected 0. 8 minus twice 3, 8 minus 6. Row 3 plus 5 row 1, minus 5 plus 5. 2 plus 5 times minus 2, 2 minus 10. minus 26 plus 15, minus 36 plus 35, and then minus 30 plus 15, and then row 4 is replaced by row 4 minus row 1. 1 minus 1, it's 0, it has to be 0. Minus 6 minus minus 2, minus 6 plus 2 is minus 4. 5 minus 3, 7 minus 7, and then minus 11 minus 3, that is minus 14. So here's our augmented matrix after one stage of the Gaussian elimination. And if we're doing Gaussian elimination, we turn a blind eye to the fact that would it be easier to write down the second equation and the fourth equation now, solve them as a 2 by 2 system, then use the third equation to find S and the first equation to find P. It's Gaussian elimination. It's a standard set of processes. We don't use this kind of judgment here. Instead, what we do now is we try to create a 0 here and a 0 here. And we do that in the second stage by subtracting off multiples of row 2. So row 1 stays the same, row 2 stays the same. We'll have row 3 minus 8 over 2 times row 2. That is row 3 plus 4 row 2. We'll have row 4 minus 4 over 2 times row 2. That is row 4 plus 2 row 2. So let's carry out those row operations. First two rows stay the same. So we have row 3 plus 4 row 2. It gives us a 0 here, as in we don't destroy this 0. We have minus 8 plus 4 times 2, minus 8 plus 8. We have minus 11 plus 4 times 4, minus 11 plus 16. We have minus 1 plus 4 times 0, stays at minus 1. And we have minus 15 plus 4 times 2, minus 15 plus 8, gives us minus 7. And then, for row 4 plus 2 row 2. Minus 4 plus twice 2, 2 plus twice 4, 2 plus 8, that's 10. 0 plus twice 0, that stays as 0. And minus 14 plus twice 2, minus 14 plus 4, that gives us minus 10. Here is our augmented matrix after two stages of Gaussian elimination. 1, 2, 3, 4, 5 zeros here. We don't count the zeros here. They are not forming part of our structure towards an upper triangular matrix. And again, under Gaussian elimination, we resist the temptation. It's a stronger temptation now to say, well, we already have an equation here. This is Gaussian elimination. We carry out the third stage, where we keep the top 3 rows as they are, and we'll take row 4 and replace it with row 4 minus a multiple of row 3. And that multiple will be 10 over 5. So we have row 4 minus twice row 3. So one more set of row operations we've identified. We'll have them taking place. So top 3 rows, no change. And the bottom row, row 4 minus twice row 3. We keep those 2 zeros. We have 10 minus twice 5, 10 minus 10. We have 0 minus twice minus 1, 0 plus 2. Yes, we've destroyed the 0 here, but it was not one of the zeros that would work hard to create. Minus 10 plus 14, that gives us 4. So now we've used Gaussian elimination to get our augmented matrix into upper triangular form. So the equations now, if we read off what the equations are, P minus 2Q plus 3R plus 7S is equal to 3. That was one of our original equations. The second equation tells us that 2Q plus 4R is equal to 2. The third equation, that 5R minus S is minus 7. And the final equation, that 2S is equal to 4. Well, it's this final equation that we look at first. 2S is equal to 4. S is therefore equal to 2. Then we move back to the third equation, which now tells us 5R minus S, so that's 5R minus 2 is minus 7. Add 2 to each side, 5R is equal to minus 5. So we get here that R is equal to minus 1. Then move back to the second equation. This one now tells us that 2Q plus 4R, well, 4R is minus 4, 2Q minus 4 is equal to 2, 2Q is equal to 6, so Q is equal to 3. And then we go back to the first equation, P minus 2Q, so that's minus 6, plus 3R, that's minus 3, plus 7S is equal to 3. 14 minus 6 minus 3, that's 5. So it gives us that P plus 5 is equal to 3. So we can now say that P is equal to minus 2. So through Gaussian elimination, we found P is minus 2, Q is 3, R is minus 1, S is equal to 2. So that is Gaussian elimination.